All right, so we've just looked at the quizzes. If you have a specific question on your paper, please feel free to bring it to me during office hours if you think I've misunderstood something that you had in your solution. And the same goes for the homework, by the way. I went through the homework assignments last night, and if in some cases there's so many different pages and so many different files, it may be that maybe it was far to the right in an Excel file somewhere, and I just didn't find the table where you've done a certain thing. So if you did the work but I didn't find it, please let me know, or if I've made a mistake, because I want you to get all the points that you're entitled to. All right, so homework 5 is due on Thursday. We're going to finish talking about evaporation today and finish up the example where we start discussing the aerodynamic method. So let's get right into that. Now, some review. I thought about having a quiz today, but I thought, well, we're going to spend so much time going through the solution from the previous quiz, we won't do it. Here's some of the questions that were going to be in today's quiz. All right? So the first question on the quiz I was going to give you for today is, what is latent heat of vaporization? Anyone want to take a stab at that? Shane, you kind of nailed it on the last quiz. What about this one? No. Guess you're glad we didn't have one today then? All right.
Is it the LV thing?
L sub V? That's how we abbreviate it, yes. So what is it? You're halfway there.
Plug into the ER.
Oh. So we're just plugging numbers into formulas, huh? See? That's why students don't like this class. All right, latent heat of vaporization is how much energy it takes to take a kilogram of water from the liquid phase to the vapor phase. So it's independent of changing a liquid's temperature. It's just the molecules need a certain amount of energy to obtain enough kinetic energy to go from liquid to vapor. And so it's a constant, although there is some temperature dependency. We'll finish up the example today, and we'll take another look at like the specific value for latent heat of vaporization. But as far as the answer, it's the amount of energy required to vaporize a kilogram of water. Okay, this one's a little easier. I only repeated this phrase about a dozen times in the lecture on Thursday last week. So there's two kinds of energy. Which one is the kind that's emitted by the Earth? Perfect, that's right, long wave. So short wave comes in, it's absorbed by the Earth's surface, and then long wave is emitted. Great. Okay, so what does the energy method that we worked the example on last time, what does it estimate in order to predict evaporation rate? It estimates how much energy is available to do the work associated with latent heat of vaporization. So it looks at the incoming short wave, the outgoing long wave, and the difference between the two is how much energy we have to do vaporization. So that's the basic idea of the energy method. Now, remember, we started our discussion of evaporation by identifying a list of factors that are going to have an effect on evaporation. And energy availability was only one of those factors. During that discussion, you rightly identified factors like humidity and wind as also having an effect. And so that's what we're going to be discussing today in the aerodynamic method, is the limiting factors associated with humidity and wind. Yeah.
Could you repeat that definition of energy method?
Yeah, the energy method is an approach that calculates how much energy is available to do the work of vaporization. And so it estimates that energy by the balance between incoming shortwave and outgoing long-wave radiation. Now there's also some reflection, but the main idea is it's an energy balance that looks at the incoming solar radiation the outgoing long-wave radiation, and says how much is left when you account for those two. You've measured the sun intensity. You have some way of predicting what the long-wave emissions are. And so how much energy is left between the two to vaporize water? Because that's what evaporation is it's vaporizing the water. And we know how many joules are required per kilogram to vaporize water. So how many joules were there, essentially? So that's the energy method. Now, aerodynamic, it says, let's turn our attention away from energy balance for a moment, and let's just look at where is that water going to go once it vaporizes? Because if the air is fully saturated with moisture, then there won't be any place for the liquid water to exit the liquid phase and enter the gas phase. Like if we had 100% humidity immediately above the water surface, then there really isn't any place that water can go. And so in the aerodynamic method, what we're asking is how quickly can that vapor be transported away from the water surface? So we want to be bringing in dry air that has a low relative humidity to make room for the water that's been vaporized. And there's a gradient that is the driving force. And the gradient, or the difference between how much water the air can hold and how much water the air is holding, is reflected by the rate. And so sometimes if the gradient is small, the rate is small. I guess one way to think about it is think about, has anybody here fasted for a couple of days before? Okay. When your stomach is completely empty, you have the ability to eat really quickly because the gradient between how full your stomach is and how full it can be is large. But then when you're filling up, the rate of intake decreases. You're not going to be eating as fast when you're almost full. And so the same thing is true of bacteria. It's essentially first-order behavior, that the rate of the reaction is influenced by the concentration. And so here what we're saying is that there's a certain amount of moisture in the air, and when you're approaching full saturation, then the evaporation is going to decrease if the gradient is small. Okay, so here is, in the first image that was already up, a side view of some water surface, and the air is coming in upwind. There was a dry fetch where it was not saturated with water. And the further away you get from the water surface, the higher the wind velocity is. And we've seen a velocity profile like this when we were talking about the no-slip condition in fluid mechanics. That is, that when you are immediately in contact with some surface that isn't moving, then the fluid above it also is not going to be moving. But then the further away you get from that stationary surface, then the velocity increases. So the more wind you have, the greater the rate of vapor transportation can be, because it's the wind that's providing air that's not saturated. Yes, Austin?
So if we're plotting the rate of evaporation versus the humidity, would it be kind of like a logarithmic relationship, kind of go to zero?
That's a good question. So let's see here. So if we have the humidity increasing, so high humidity we would expect, and here on the vertical scale is evaporation, we would expect for high humidity the evaporation would be low, right? And low humidity the evaporation would be high. So it probably looks like that. Yeah, this is a first order curve where it wouldn't be linear. The other factor that plays into the aerodynamic method is that as you get further away from the surface, remember that the air is cooling because of the dry adiabatic lapse rate, which is just that as you go up through the atmosphere, the pressure is lower, and so gases are expanding, and as those gases expand, they cool, and so at some elevation, the temperature is lower. And the more you have a large difference in temperature, then the greater the difference is going to be between the saturated vapor pressure, which means how much moisture can be in the air, and then the ambient vapor pressure. Vapor pressure is just a way of describing how much moisture is in the air. It's another way in addition to relative humidity. So relative humidity is expressed in terms of a percentage, just like a percentage of how much moisture could be at a certain temperature dissolved in the air. But vapor pressure isn't a percentage scale, it's more of an absolute scale, measured in the same units of pascals or newtons per meter squared that atmospheric pressure is measured with. And so what we're saying here is that if you have a big temperature difference between the water and the air, then you're going to have a greater difference between the amount of moisture that can be held in the air and how much is in the air. And specific humidity is just for a certain temperature how much moisture can be held. And so it's similar to relative humidity, except for that it is normalized across temperature, whereas relative humidity is not. So let me show you how we actually go through the process of calculating this. The equations are presented from top to bottom in the order that you'd need to go through them. Actually, I think it's from bottom to top, now that I think of it. In a problem statement, you're going to have to estimate the evaporation rate using, first of all, knowing the air temperature. You'd need to know the roughness height of the water. And the reason why you'll be told how big the waves are in the aerodynamic method is that if you have a smooth, glassy water surface, then there is less surface area for the evaporation to occur, whereas if there are ripples, like are shown here, the cross-sectional area that the water is evaporating over would be larger, the more waves there are. Yeah?
What did you say the difference was between saturated vapor pressure and ambient?
Ambient vapor pressure is like the conditions that are in the atmosphere actually. Saturated is the maximum amount of water that can be held by the air. So if you have a big temperature difference between the water and the air, then that lends itself to there being a larger difference between how much moisture can be held and how much moisture is in the air at any given time. Okay, so some of the things that you'll be told in a problem statement where you're doing the aerodynamic method is you'll be told the air temperature, you'll be told how windy it is for obvious reasons because you have to know how quickly the moisture is moving away from that water surface. The roughness of the water, so the wave height, more wave height improves evaporation rate. The relative humidity is going to be a factor, and then you're given some atmospheric conditions. So you'll be told what's the ambient vapor pressure, the saturation vapor pressure, or given a formula that allows you to estimate that based on the air temperature. All right, so the same illustration that we looked at before where we had this inland lagoon, and we're trying to find out on a day where we know the certain amount of radiation intensity and the air temperature and the water temperature and so on. Let me walk you through what we would do for the aerodynamic method here. We're not going to need to know any of the radiation intensity for this part. First of all, we'll take a look at E sub AS. Now, this is where we're trying to calculate, based on the air temperature, what is the partial pressure of moisture in the atmosphere. And so this is just an estimate based on the temperature in Celsius. Now, I know it's confusing. Sometimes we, in problems like this, have to convert into Kelvin. Sometimes we can leave it in Celsius. This is one where you can leave it in Celsius. So 17.27 times 28.5, which is the given air temperature, and 237.3 plus 28.5 Okay, so that tells us that the E sub AS is 3893 pascals. That is the maximum amount of moisture that can be held by the atmosphere. So saturation vapor pressure. So when you've got air that's 28.5 Celsius, then, you know, if sea level pressure is 101,325 Pascal, what we're saying is, of that 101,325, 3,893 pascals could be water vapor. I mean, the rest of it, we know there's a lot of nitrogen, oxygen, and then other gases like CO2 and noble gases like helium, hydrogen, and so on. So water will be a small fraction of the overall pressure, but this is saturation. At most, it's going to be 3893 pascals. Okay, so the relative humidity is 75%. That's something that you can measure with just a meter that you could pick up from Walmart. You know, relative humidity meters are kind of a dime a dozen. So the E sub A is the actual vapor pressure, and so it is the E sub AS times the relative humidity. Okay, so we know that maximally there could be 3893 pascals, and the vapor pressure is 0.5, I'm sorry, the relative humidity is 55%, so we multiply that by 0.55, so it's 2141 pascals. Oh, 75? Okay, thanks for noticing that. So let me check if I had just written that wrong or if I'd calculated it wrong too. Let's see. All right. So let's fix that. 0.75 times 3893. Okay, so it should be 2919.75 pascals. Thank you for noticing that. Okay. 2919.75 pascals. Okay. The other thing we need to know, first of all, the wind speed. So the wind speed is 2.7 meters per second, and that's measured at a certain elevation. It's measured at an elevation above the water surface of 2 meters. So Z2 is 2 meters. And the height of the roughness elements, meaning the wave height, is 0.03 centimeters. So it's relatively low wave height. Okay, with that, we calculate B, and it's 0.102 divided by the logarithm of Z2 divided by Z0 squared by U2. Yeah, thank you. Okay, so 0.102 times 2.7 meters per second, and divide that by,
And that's 1.7 meters per square meters over.
which one?
The wind speed.
The wind speed. 1.7 meters. Yep, you're right. Boy, I wonder if these are old calculations. Guess I just didn't update it. All right, yes, 1.7 is the wind speed. Thank you for noticing that. 1.7. All right, and then we need to have the ratio of the elevations in the denominator. So Z2 to Z0, so that's 2 to 0.03. Okay, and then we square that. Centimeters and, yeah, meters. Yep, we do. So 200 centimeters and 0.03. All right. So 0.102 times 1.7 200.03. All right, so if anybody else also did these calculations, do you get 0.002237? All right, good, thank you. That is, and the units there are millimeters per day Pascal. So 0.002237 millimeters per day Pascal. That's called the vapor transfer coefficient. And then finally, once we have that vapor transfer coefficient, we calculate the evaporation rate by B times E sub AS minus E sub A. So the difference between the two is the gradient. And remember, a big gradient is what causes a fast evaporation rate. So we're looking at how far apart is the amount of moisture that's in the air compared to how much can be in the air. So we'll multiply 0.002237 millimeters per day Pascal by the difference in the pressures. And so it is 3893 pascals minus 2919.75 pascals. So 2.18 millimeters per day. Anybody else get that same value? Yeah. All right, great. Now, if you remember what the energy method, I know what happened. I changed this example last year just to make the difference more dramatic. So this is saying that when we look at the rate of vapor transport by itself, just the rate of vapor transport, we're estimating that evaporation rate will be 2.18 millimeters per day. When we looked at the energy method in our previous example, it was predicting that we would lose 6.55 millimeters per day. And so we have to figure out which is right. You know, where is it? Is it 6.5 millimeters per day when you look at the available energy, or is it 2.2 millimeters per day when you look at the available transport? And so the combined method kind of says we're going to have to average the two in a way. We need a method to come up with a weighted average. We don't have unlimited energy. If we did have unlimited energy, then you'd use the aerodynamic method because the limiting factor would be transport of the vapor. If you had unlimited transport, then you'd use the energy balance method because you just You'd be able to move all of the air away from the water surface, but you'd just need to know how much energy there was to actually do the latent heat of vaporization. Either case is pretty rare. It's not going to be common where you have unlimited energy or unlimited transport. So the combined method allows us to come up with a weighted average between the energy method and the aerodynamic method. And it uses these averaging coefficients that that vary based on the air temperature and based on this psychometric constant, which is slightly affected by the temperature of the water, because the latent heat of vaporization varies based on the temperature of the water. This full combined method, it doesn't add too much complexity to the problem, although you have to know like the molecular weight ratio for air and water. To get around having to do all this, it was observed in the Priestley-Taylor method that it's about 1.3 times this ratio times the energy balance method. That in many cases you can get about the same value by multiplying this ratio by the E sub r. So let's try that. Let's use both the combined method and the Priestley-Taylor method, where we have this E sub a of 2.18. The E sub r from our previous example, let me write that down. So it was 6.55 millimeters per day. So E sub r was 6.55 millimeters per day in the previous example. Let me stop talking and give you a chance to calculate this. You can work with your classmates or do it individually as you prefer, but what you'll need to do is calculate the delta factor, and then for the psychometric constant, we're just going to use, for gamma, 66.8 pascals per degrees Celsius. Now, the delta, though, you will have to calculate based on the E sub as and the T sub a. And so the E sub as that we used was, let's see, E sub as was 3893 pascals, and then the air temperature is 28.5 degrees Celsius. The reason why the Priestley-Taylor is available as an estimation, that would be used in situations where you don't have the data that you need to calculate E sub a. So if you didn't have estimations of the wind speed, if you didn't have estimations of the relative humidity, and basically all of the information you need for the E sub a, if it wasn't available, then the Priestley-Taylor can be used as a substitute, but it didn't really do much beyond just the energy balance method in this case. I mean, the input value for energy balance was 6.55, and just because of the air temperature conditions we have, that's the primary factor that goes into the delta. Then Priestley-Taylor didn't give us much of a different answer than just the energy balance by itself. Yeah.
Do you think we could just change that formula to be -1? I don't know if that works for every condition, but if you subtract 1 from it, it's almost exactly the same.
I don't know. I'd need to look at it over a wider range of conditions. Yeah, I'd want to try like lots of different relative humidities and so on. I think if it was that easy, they probably would have figured that out, but maybe not.
Maybe not.
There could be the Austin Page method.
Because a millimeter per day, if you have a certain threshold, say you've got a flooding and you've evacuated a bunch of people, and you're thinking, okay, how long is it going to take to evaporate? That's a day's difference. So, holding them somewhere else before they can come back in.
Yeah.
Between the two methods, you've got.
Yeah. Yeah, the main application for situations like this is actually like crops and agricultural uses rather than flooding. But yeah, the simpler your method is, the better. That's for sure. Let's talk about crops and evaporation, because there's a direct way to measure evaporation rather than having to estimate how much it might be based on wind conditions and air pressure and so on. You can set a pan out and measure how much the water is going down in the pan. It's kind of like the inverse of a rain gauge. A rain gauge is you're setting out a pan and you're watching the water level accumulate as the water falls into it. An evaporation pan is you set a body of a known amount of water out, and if it's windy or if there's lots of sun, those are things that will promote the evaporation, and then it will be observed by a decrease in the depth. And of course, you'd need to keep track of how much precipitation there is. And so, if your water level stayed constant, but there was an inch of rain, then you'd know, well, there must have been an inch of evaporation and an inch of rainfall if it stayed constant and I knew how much rainfall there was. And so pans like this do take into account the difference between what's coming in and where the water levels are at. Did you have a question? Rainfall? Yeah. So you can set a pan out in a field of some sort, whether it's like turf or crops. There are also evaporation pans that are set out on water bodies, so that if they are measuring how much evaporation there is in some sort of like a small plastic pool that's inside of the lake, then they can use that to extrapolate how much evaporation there was in the lake more generally. And so, keeping track of the entire lake would be more challenging than just keeping track of what's happening inside of this controlled volume, because there could be streams coming into the lake, but there wouldn't be any additions to this known amount of water other than precipitation, which can be measured. But there wouldn't be inflows from like a creek or there could be into the lake generally. There could be base flow additions where groundwater is seeping into the reservoir, but there wouldn't be that since it's going to be like a plastic-lined tub of some sort. So they're just measuring the water level and how much rainfall there is. The biggest application of this is to estimate evapotranspiration. And those two terms are combined together in the case of crops because evaporation and transpiration are difficult to distinguish between the two of them from an experimental standpoint. Transpiration is the amount of water that is being exhaled by the plant surface area. So just like how humans sweat and lose moisture off of our skin, plants do the same thing. They, in the process of giving off oxygen, taking in carbon dioxide, they also lose water. So if the main application is to use this pan to predict how much evapotranspiration there is in a crop, what they do is they'll set out a pan and they'll measure what's happening to the pan, And then there are known coefficients that relates the pan performance to the performance of different types of crops. And so this table is for a short green crop in case A, this data. Case B is for dry, bare earth. And so what you would be relating is what happens to the pan relative to what happens to the crop or soil type of interest. And so if we just look at some of the trends here, what you'll notice is that if you have high humidity, so in the case of high humidity, then the pan behavior is more closely related to the behavior of the crop. So the evapotranspiration is going to be the evaporation from the pan, E sub P, multiplied by this K value. And these are the K values, these decimal 0.55, and I guess as high as it gets here is 0.85. So what it's saying is that the evapotranspiration is going to be 85% of the pan evaporation if you have high humidity, and upstream of the crop, upwind of the pan is a certain amount of crop. So this is getting at where is the pan located within the crop that you're trying to predict the evapotranspiration for. Farmers care about the amount of evapotranspiration because then it tells them how much additional irrigation may need to be added. So let's say that you've got this agricultural field of corn, and the wind is blowing this way. If you have your pan just at the upwind end, then this may be dry air that's coming, and so that there would be more evaporation when the dry air encounters the pan. But now consider, what if the pan was downwind so that upwind of it was the crop? So you have dry air encountering the crop, and so the crop is emitting moisture and going to, in theory, because of all the moisture the crop is emitting, saturate the air so that by the time it gets to the pan, there would be relatively less evaporation from the pan. And so what this table is saying is that you need to kind of identify how much upwind crop there is before the pan. And so if there is less upwind, then you're going to see the evapotranspiration would be a smaller fraction of the pan evaporation. So the K value would be different. Of course, the wind conditions are also reflected in here. And so let's practice that by looking at, in Northeast Ohio, an average wind speed would be 2.7 meters per second, and the mean relative humidity is 65%. Okay, so the wind velocity is 2.7 meters per second, and the relative humidity is 65%. So we'll use that and come back to the table to get the right K value. The pan itself is measuring 4.2 millimeters of evaporation per day. So that's the E sub P is 4.2 millimeters per day. So the question is, if we have this this pan set up and we want to consider what's happening for short irrigated grass turf on a monthly basis. So how much evapotranspiration would there be for grass in a month if we have this pan that's surrounded by 100 meters of dry fallow on all sides? Okay, so the pan in this case is surrounded by dry fallow, and we want to know what is the correct K value to use. Okay, so it's not surrounded by short green crop. We have our pan, for whatever reason, put in a fallow area. So we need to have, for the moderate wind speed, since our wind was 2.7 meters per second, we're in the moderate wind speed, and it has 100 meters on all sides of fallow, and the relative humidity was 65%, so that puts us in the medium range. That tells us the K sub P should be 0.6. So K sub P of 0.60 means that the actual evapotranspiration is going to be 60% of what the pan is experiencing. Okay, so E sub T naught is 0.60 of the 4.2 millimeters per day. And then we want to multiply that by 30 days per month to find out the monthly evapotranspiration that would be experienced. So 0.6, 4.2, and 30. 75.6 millimeters of evapotranspiration per month. So this is a table that would allow you to predict the evapotranspiration of grass depending on where the pan is located. Our pan was surrounded by fallow, and this is a reference table that's specific for grass behavior. But the second part of this in-class exercise says, so what if the crop was corn instead of grass? Would we need to be worried about there being more evapotranspiration, or might there be less? And in just a moment, I'll show you a table that relates different types of crops. Austin, do you have another question?
Yeah. Could you also measure the transpiration by having two pans in the direction of wind, one before the crop and one after the crop? That way you can see the difference in evaporation rate between the transpiration.
That might be one way of looking at it, but remember there could also be, like if we had an upwind and a downwind, then some of the moisture might be going up rather than just only side to side. Like if we're saying that the difference between the two is fully accounted for by the evapotranspiration that happened in the crop, then we'd have to have one-dimensional flow to be able to do that. And some of the evaporation, the moisture could be going up, it could be going side to side. So there's something to that idea, but it maybe wouldn't be definitive. What this figure shows is how, when you use grass as a reference, how other types of crops may use usually more, sometimes use less water than a reference crop of grass. And so in the case of corn, maize in this figure, you may need 30%, 40% more water to satisfy the evapotranspiration. There are a few crops where the water demand is lower because there's less evapotranspiration, but what you'll notice is that most of those crops where it's less than a 1.0 K value are tree crops. So apples, cherries, peaches, citrus, those are all crops where the fruit is concentrated rather than being a more broadly distributed, like sugarcane or maize or things that have a lot of leaf area. So just kind of interesting. There are tables out there that relate K values based on the performance of grass. Okay, well that's all I have for you today. I'll see you in class on Thursday, and I'll bring some information about the exam when we have that class meeting. I'll see you then.